This is problem number 13. You're designing a rectangular poster, needs to contain 50 square inches of printing, has a 4-inch margin at the top, 4-inch margin at the bottom, 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? So we'll sketch this out first to see if we can figure out what they're talking about here. We have some kind of a rectangular poster, but it has fairly large margins. And so inside here we actually have the printing. And at the top we have a 4-inch margin. The bottom we have a 4-inch margin. And here's where we have our printing. And the side we have a 2-inch margin and a 2-inch margin. So that's kind of the setup for our problem. But overall dimensions will minimize the amount of paper used. And there's a couple approaches to this. You could have your overall dimensions be x and y. And actually, I'm going to prefer, I've done this problem before, so I know it'll work out slightly nicer, if I call my inner dimensions. I'll call that x, that inner dimension, and this inner dimension y. Hopefully you can see that a little bit. But we're going to have y going that way. So, I zoom in. I want to minimize the amount of paper used, the overall paper, not just the printed area, but the whole big blue paper here is what I'm going to minimize. So minimize the amount of paper used. I'll call that A for the amount of paper. And I know they're just talking about the amount of paper means the area of the paper. Well, if my space here, if it's going up and down x, my height would be x plus the 4-inch margin at the top, the 4-inch margin on the bottom. It'd be x plus 8. Going up and down. And coming across, I have these 2-inch side margins. So 2 plus 2, it'd be y plus 4 going the other way. So I've got my area is x plus 8 times y plus 4. That's the equation I'm going to focus in on because it said minimize the amount of paper used. I see the two variables. I know with two variables, I can't take this, so I want to somehow get rid of one of the variables. And I look up here and I notice there's 50 square inches of printing. So that's the red part. Right in here, we've got that red part. So on the side, I have 50 square inches. And that rectangle there would be x times y. Take your pick. It doesn't matter which one you solve for. I'll solve for y. And y is 50 over x. So I come back now to my area equation. Area is x plus 8. I'll take out the y. I'll put in 50 over x plus 4. Let's FOIL this out. When I FOIL out the first, the x's cancel out. I get a 50. The outside gives me a 4x. The inside gives me 400 over x. And last gives me 32. A good algebra student would combine like terms, but I know I'm going to maximize or minimize this. I know I'm going to take the derivative. So I'm going to take the derivative knowing that the constants go away anyway. I'll take the derivative. The 4x goes to 4. 400 over x becomes minus 400 over x squared. And I immediately note a critical point. One critical point is where my derivative is undefined. And that critical point is x equals 0. Very exciting, but that's not really in the domain. How could you have a width of 0? So it's a critical point, but not within this problem. It's not in the domain. And what would the domain be? Well, x would certainly be bigger than 0. And in terms of a maximum, you could make x to have an area of 50. You could make x anything you want it to be. It could be 50 million, and then the y, the width would be 1 millionth. And 50 million times 1 millionth would be 50. So there is no real upper bound to x. So we don't really have any endpoints in this problem. Hopefully we'll only have one critical point, and that one critical point will be our max, our min. Certainly x is positive. It wouldn't make sense to have a negative dimension. So we come back over here. We have our first derivative. We set it equal to 0. We put the 400 over x squared on the other side. We can cross multiply or take a reciprocal or whatever you want to do here. But 4x squared is 400. X squared is 100. So x is 10. Now I'm not worried about the negative 10 because the negative 10 wouldn't make sense in this problem. We're having measurements here, and our measurements are going to be positive measurements. Okay, is this 10 a max or is it a min? Let's go with the second derivative test this time. I'm kind of jumping back and forth on the problems. I'll take the second derivative, a double prime. The 4 goes away. And now this x to the negative 2, if I bring that power, I get 800 over x cubed. And I can see for any positive x, a double prime will be positive, but let's just put in the 10 anyway. So our second derivative at 10 will be 800 over 10 cubed, so that's 8/10 or 4/5. And that is certainly positive. Our second derivative is positive, so what have we done? We found the only critical point in our domain is a local min. All right, let's answer the questions. What overall dimensions? And don't forget, we need to come back here. Overall dimensions are x plus 8, y plus 4. X plus 8, y plus 4. And if x is 10, 10 plus 8 will give us 18. So our dimensions here, so 10 plus 8, our overall will be 18. And then y, we need to come way back over here. Y is 50 over x. 50 over 10 is 5. So y is 5. And I come back here, my actual width is y plus 4. 5 plus 4 is 9. So the overall dimensions are 18 by 9, and these were inches. 18 inches by 9 inches. All right, what overall dimensions will minimize the amount of paper used? We've answered it. An 18 by 9 sheet of paper will minimize the amount of paper used. That completes problem 15. Problem 13, sorry about that.